In our next Notepack lesson called Calculating Equilibrium Constants, we'll be practicing the very skill of products over reactants to determine the KEQ, the equilibrium constant, to look for the magnitude of the number. Knowing the larger the number, the more the products are being favored. The smaller the number, less than 1, the reactants are being favored. And we introduce a concept known as an ICE chart, ICE, the initial, the change, and the equilibrium concentrations of our reactants and products, knowing that ultimately when we calculate an equilibrium expression, we must have the E, the equilibrium constant values. What did we start with? How much did the concentrations change by, and what did they end up with at equilibrium? We'll start with the very first problem, an example. Calculating a K when all equilibrium concentrations are known. So let me read the question with you. We have a mixture of hydrogen and nitrogen in a reaction vessel, and it's allowed to attain an equilibrium at 472 Celsius degrees. The equilibrium mixture of gases was analyzed and found they had 7.38 atmosphere hydrogen, 2.48 atmosphere nitrogen, and 0.166 atmosphere ammonia. Let's calculate the Kp. Well, first, as any good chemist does, we write our equation. This is the Haber process, where the molecular nitrogen combines with molecular hydrogen, and we form an equilibrium for the production of ammonia. All of these are in the gaseous phase. What we're noticing very nicely is that every one of these are at equilibrium. The equilibrium mixture was analyzed to find. So what we're really being given are indeed the values at equilibrium. So remember, these are Kp's. So Kp would be the partial pressure of ammonia, NH3. You know what we didn't do? We didn't balance. Let me go back. We have two ends. We'll need to double here. 3, 6, 1 to 3 to 2 stoichiometric ratio. So now when I consider we have the partial pressure of ammonia, that it will indeed need to be squared, set over the partial pressure of nitrogen and the partial pressure of hydrogen, and indeed those values taken to their stoichiometric value, first order with respect to N2, and this hydrogen would need to be cubed. So now it's just a plug and chug. We're given that information for each one of these. 7.38 atmospheres of hydrogen was its given value. 2.46 atmospheres for nitrogen, and 0.166 atmospheres of ammonia. Let's plug our values in and solve for our problem. 0.166, the value in atmospheres, squared, set over the 2.46 atmospheres for the nitrogen partial pressure, and hydrogen was given to us with the first value of 7.38, and it would need to be cubed. Let's hit together, make sure we get a common answer, and see what we find. So I'm going to grab my calculator. I'm going to hit 0.166 squared divided by 2.46, divide again by 7.38 cubed. And my calculator gives me a value of 2.79, I'll round a little bit, times 10 to the negative 5th value. And remember that Kp, no units on our equilibrium values. That's not very neat. 2.79 times 10 to the negative 5th, the value of Kp. Now make a note here. Equilibrium constants were given. Equilibrium values given, so it's just really a plug and chug. So what makes the next problem a little bit different? Let's take a peek. Sometimes we're not given the actual equilibrium values. So oftentimes the equilibrium concentrations of all chemical species are not known, but we can deduce those given some vital information. The first is that stoichiometry helps us deduce the concentrations. Stoichiometry are the powers with which we'll end up raising our values. So stoichiometry helps us deduce the concentrations at equilibrium. We're going to tabulate, and keep in mind I'm kind of giving us a prelude into this lesson called an ice chart. We need the initial, the change, and the values at equilibrium. We'll tabulate all known initial and equilibrium concentrations of the species that appear in our equilibrium constant expression. Remember that pure solids and pure liquids would indeed fall out of the expression. No need to calculate them. And for those species for which both the initial and the equilibrium concentrations are known, we can calculating using stoichiometry the change in the concentration for any other reactant or product that's yet to be determined using our ice chart. So we'll start with what we know, filling in a table known as ICE. Our third step, of course, we'll use the stoichiometric ratios of reactants and products to calculate the changes in concentration for all of the other species in equilibrium, and from there complete our chart. From all the initials and changes, we can then deduce the equilibrium concentrations. What I've just described to you in a four-step process is an ice chart. Filling in a grid for all reactants and products, what do we know in terms of the initial and equilibrium values, and deducing using stoichiometry any other missing tabulated area to find the row we need to calculate KEQ. Let's take a practice. Read this with me. We're on page 7 of your notes. We have a closed system initially containing, now there's a very important keyword, initially containing hydrogen gas and iodine gas, and it's allowed to reach equilibrium. Analysis of that equilibrium mixture shows the concentration of the combination reaction is the provided value. Calculate Kc, these are molarity values. Begin with me by tabulating what we know. First, we're going to need a chemical equation, aren't we? So the chemical equation, let me bring that back. I've lost the spot. Please be patient with me as I find the spot we just left off. There, we got it. Thank you. All right, so a little technology, isn't that fun? We have the following equation. Hydrogen and iodine are allowed to reach equilibrium. So H2 and I2 are both diatomics. We have an equilibrium set up. Of course, we can see the expression would be the production of HI, a simple combination reaction. Tabulate with me what we know. We know some initial, we know the change, and the equilibrium concentrations. And I'm beginning with you the very first time something known as an ice chart. So here I am for each one of our reactants and products. I need to tabulate the information given to me. We know, and very important key word, the initial concentrations of the reactants. Initially containing, so notice I'm down here at I for initial, 1 times 10 to the negative third molar unit hydrogen, 2 times 10 to the negative third molar concentration of iodine, and it's allowed to reach equilibrium, and the product concentration is given to me. The product concentration is 1.87, that's down here, 1.87 times 10 to the negative third molar unit. Initially, the reaction is charged with 1 times 10 to the negative third hydrogen, 2 times 10 to the negative third iodine. You know what else we know? That initially there's absolutely no product. the reaction hasn't started yet, so there is no product. So go ahead and fill in that we know there's 0 molar product. Time goes by and reactants get used and products get made. How much does the product change by? And that's what this is here. It changes by. So in green, this is the supplied information. Let me just switch color and just kind of keep alrighty. I'm going to keep in red. I'm trying to get rid of that. Thank you. What we now have to tabulate. So of course products get made. If we started with 0 and at the equilibrium process we're now at 1.87, that product increased by a value of 1.87 times 10 to the negative third molar unit. So we had an increase of product. But you know what? Reactants get used. Their value decreases. And look at the stoichiometry. We have a 1:1 to 2 ratio. Stoichiometry, the little heart of our problem, is want over given. For every 2 moles of HI that is made, we only use 1 iodine and 1 hydrogen. So let's figure out, or tabulate if you will, how much the concentrations of each reactant change by. 1/2 of 1.87. Want over given. I want iodine from HI. 1/2 of 0.187. 1.87 E negative 3 divided by 2 gives me a value of 9.35 times 10 to the negative fourth. It would be exactly the same number here, 1/2 of 1.87. They are both used in equal quantities. Let's tabulate. If iodine and hydrogen get consumed with a 1:1 mole ratio, producing twice the quantity of HI, that's what this change is. A 1:1 makes 2. Let's subtract and see the quantities remaining of our reactants. So I'm going to hit 1E negative 3 minus 9.35 E negative 4, and the quantity remaining of hydrogen is 6.5 times 10 to the negative fifth molar units. Let's subtract to find the equilibrium concentration of iodine. 2E negative 3 minus 9.35 E negative 4, and I get a value of 0.001065 molar units. We now have the values we need in order to calculate our Kc. Ultimately, that's what we're trying to calculate. So Kc is an expression that would show the molar concentration of HI squared due to its coefficient of 2 times the molar concentration of the molecular hydrogen and the molecular iodine. And we have these values now right here in the equilibrium in the ice table. We have 1.87 times 10 to the negative third. That needs to be squared. Set over 6.5 times 10 to the negative fifth times 0.001065, that concentration from the iodine. Hit with me, make sure we get a common answer. 1.87 E negative 3 squared keep hitting with me. E negative 3 divided by 6.5 E negative 5, and divide again by 0.001065. And did you, like me, I hope, find an answer and I'll write that out in green, 50.51. And so our Kc value that we calculated very first time we've used an ice chart, 50.5, very much favoring the product side of our equation. Let's recap. In this particular problem, we introduced the first time an ice chart. We were given information about the initial concentrations of the reactant, and we were given information about the equilibrium concentration of the product. From there, we used stoichiometry to calculate the change in the concentrations of all reactants and products, and therefore able to tabulate the remaining equilibrium concentrations and use those to calculate our Kc. Let's keep going, trying a next one. Here we have sulfur trioxide decomposing in a sealed container to give gaseous sulfur dioxide and oxygen gas. We did balance here. Let's try two S's. 4 plus 2 is 6. There we have it. So there's our equation from that very first sentence. Alrighty. It says initially the vessel is charged at 1,000 Kelvin units with SO3 at a partial pressure of 0.5 atmospheres. My initial pressure of SO3 is 0.5. The equilibrium of SO3 partial pressure is 0.2 atmospheres. Calculate the Kp at 1,000 Kelvin units. So here's the information we were given, and I'm just getting the start of my ice chart. Here we're given the initial pressure of SO3 and the equilibrium pressure of SO3. We can clearly see that it has decreased by a value of 0.3 atmospheres. We also know that there are no products in the initial equation, so we know that the value of their pressure is at 0 atmospheres. If SO3 decreases, it's a reactant, so it's consumed. The ratio here, 2 to 2, is the same number, isn't it? So this is going to increase with the same partial pressure of 0.3. Adding that, we get an equilibrium value of 0.3. But here we have 1/2 of 0.3, which is 0.15. Notice that's 1/2 of 0.3. And so here we have a value of 0.15 at equilibrium. 0.15, the partial pressure in atmospheres of oxygen. 0.3, the partial pressure of SO2 in atmospheres. And 0.2, the partial pressure of our original reactant at equilibrium, are the values we need to calculate the Kp. The Kp is an expression, products over reactants. Our products, SO2, its partial pressure would need to be squared, times the partial pressure of oxygen to the first power, set over the partial pressure of sulfur trioxide, all squared as well. And let's just plug those numbers in and see what we find for our answer. SO2 is 0.3 squared. Oxygen is 0.15 set over 0.2, which needs to also be squared. Now please hit with me to be sure we have a common answer. 0.3 squared times 0.15 equal, divided by 0.2 squared, and I'm finding a value of 0.3375. No units for Kp. That is a number smaller than 1, so we know that the reactant is being favored in the equilibrium. Our lessons continue with our next section in our equilibrium chapter, known as the reaction quotient Q. What this is just a variable that lets us know the direction that the reaction is heading towards as it's trying to achieve equilibrium. It's calculated the exact same way as our KEQ, the equilibrium constant, but for a system that's not yet achieved equilibrium status. So Q is products over reactants, where the coefficients become the power with which we raise our molarity concentration units. And it's a number. The number that we get is a Q, a quotient, which just means that we're dividing products over reactants. And it's the size of the number that becomes important to us as we decide, is this equation proceeding towards the products heading to the right? Or is the reaction proceeding back to the reactants? We say that's heading left. It's not yet achieved the equilibrium status, but the number allows us to predict if it's heading to the right or to the left. So let's suppose we go through a calculation and we come up with a reaction quotient, the letter Q, and we compare the size of that number to the known equilibrium constant. If we calculate the ratio of the products over reactants and the Q comes out smaller than the K, and again this would be known, it's told to us in the either the problem or in a reference table, and if the magnitude of the Q is not large enough, we know that there's not enough products, that the reaction is on the right, shifting to the right to make more products until eventually the Q and the K are indeed the same number. Suppose you go through calculations and the Q comes out too large as compared to the known K constant. What do we now know? Well, if Q is larger than the known equilibrium constant, what we'll end up doing is saying that the products need to be greater than, so we're going to be reducing them, shifting to the left. If the number is too large, we have too many products, let's use those up and shift to the left. And eventually, when Q is exactly the same as K, we know that the system is indeed at the established equilibrium. If K is too small, we need more product, head to the right. If Q is too big, we have too many products, shift to the left, make the number smaller when we take products over reactants. The reaction quotient is a number. It's a number that we use to compare to the known equilibrium constant to make the decision, are we at equilibrium, if they're the same number? Are we heading to the right, Q is smaller than K, or are we heading to the left, where Q is larger than K? Let's take an example. It says for the reaction NOCl in dynamic equilibrium with 2 units of NO plus Cl2, the equilibrium constant is given to us, 1.55 times 10 to the negative fifth. That equilibrium would have absolutely no unit, so that should be crossed out at 35 Celsius degrees. In an experiment, we have 0.1 mole NOCl, 0.001 mole NO, and 0.0001 mole of chlorine, and they're mixed together in a 2-liter flask. Which direction is this equilibrium proceeding as it establishes the K constant? Which direction is the reaction proceeding to achieve equilibrium? Well, let's begin with an expression for the reaction quotient. The reaction quotient is calculated exactly the same way, except it's not called a K because we're not at equilibrium, we're on our way. So the concentration of our product, which would be NO, which would be squared due to its coefficient of 2, times the concentration of chlorine, which is Cl2, its power of 1, set over the concentration of NOCl, which would be squared due to its stoichiometry, a 2 to 2 to 1 ratio. What goes inside, we know those brackets stand for molarity. So NOCl is the bottom number. It's the first number given to us, 0.1 mole, in a 2-liter flask, there's its molarity, moles per liter, which of course needs to be squared. The next number given to us is the NO, which is also squared, so 0.001 mole per liter. Which is also squared. And the last number given to us, 0.0001, and that's moles per liter. And that's to the first order. I'm going to take my calculator and hit that. I'm asking you to do the same so that we know we got a common answer. Parenthesis 0.001 divided by 2, close parenthesis, squared, times parenthesis 0.0001 divided by 2, close parenthesis, divided by new parenthesis 0.1 divided by 2, close parenthesis, squared. And we get a number, and that number that I have on my calculator reads 5 times 10 to the negative 9th, and that's no unit, it's the number we call Q, the reaction quotient. Q is equal to 5 times 10 to the negative 9th. Now let's compare that. The K was 1.55 times 10 to the negative 5th. And so therefore, this Q compared to the magnitude of K, of course, is much smaller. And so what have we learned about the proceedings of our equilibrium? Remember that? If Q is smaller than K, we don't have enough product, so it's shifting to the right. It needs to make more product to get that number larger. So we now know if Q is smaller than K, it is shifting to the right. We need to make more product, make the number up here larger to get the Q in line with the known K. Calculating equilibrium concentrations, we've done a few practice problems here using an ice chart as well, and I believe this one will come in handy too. For the Haber process, which is used for the production of ammonia at 500 Celsius degree, has a Kp known as 1.45 times 10 to the negative 5th. In an equilibrium mixture of the three gases at 500 Celsius, the partial pressure of hydrogen is given and that of nitrogen is given. What's the partial pressure of ammonia in the equilibrium mixture? Well, we'll need to do some work. First, let's think about our balanced equation. We know that we have molecular nitrogen combining with molecular hydrogen in dynamic equilibrium for the production of our molecule ammonia, NH3. To balance our equation, we have a 1 to 3 to 2 stoichiometric ratio. There is no need for an ice chart. I misspoke because I read this right away. I know equilibrium mixtures are given, and we have what's called a Kp. The Kp was given to us as well, which is 1.45 times 10 to the negative 5th. And so we know the following. We have an equilibrium mixture already achieved. Hydrogen is at 0.928. I'm just going to tabulate what I know, and those are atmospheres. Nitrogen is at 0.432. And we know a Kp. What is the partial pressure of ammonia in our equilibrium mixture? Should we just call that X? Kp is an expression that can be used to calculate by using the partial pressure of ammonia, NH3. and of course that needs to be squared due to its coefficient, set over the partial pressure of molecular nitrogen times the partial pressure of molecular hydrogen cubed. Here's the variables that we know. The Kp was given 1.45 times 10 to the negative fifth power equals, ammonia is what we're looking for, so let's put that in as a value of x. We know that x will need to be squared. It's a power of 2. Set over the partial pressure of nitrogen given to us is 0.432 times the partial pressure of hydrogen, which would need to be cubed, so 0.928 cubed. So let's pull out for our calculator here, and we're going to cross multiply and end up taking a square root value to pull out and isolate our variable x. So my key sequence, 1.45 e to the negative fifth power times 0.432 times 0.928 cubed equals, and my screen right now says 5 times 10 to the negative sixth, but remember that's x squared, so square root that, square root my answer, and my value for x is 0.0022 atmospheres. The partial pressure of ammonia at equilibrium. Given a Kp and 2 of the 3 ingredients, we were able to set up an expression where the partial pressure for ammonia was our targeted variable. Kp times nitrogen's pressure times hydrogen's pressure cubed equaled x squared, so I square root that value and found my partial pressure of ammonia at equilibrium. What if we are calculating equilibrium concentrations from initial concentrations? We end up using something called the quadratic equation, which I happen to have a program in my calculator, and I'm sure you do, or if you don't just yet, I would be happy to transfer that to you during class time. Let's take a peek. We have a liter flask, which is nice. Now the moles per liter is directly molarity. Hydrogen and iodine. And let's kind of start tabulating what we know. So we have a reaction vessel where we have hydrogen gas. I'm going to write that out as H2, molecular hydrogen. And iodine gas is also molecular form, so I2, setting up a dynamic equilibrium for this combination reaction, 2 units of HI. Now, thinking about this word here, it's charged with, it's filled with, what that's telling us is its initial concentration. So we have the beginnings of an ice chart. We have 1 mole of hydrogen initially being charged with 2 moles of iodine initially. And of course we know that there'd be 0 moles of product. Product has not yet been made if the reaction is yet to start off. The other interesting piece of information, it says they're giving us the Kc for this combination reaction, 50.5. Kc is a value that is known, 50.5. What are the concentrations for the reactants and products at equilibrium? So let's calculate the E row. We'd like to solve for the equilibrium concentrations, knowing that their values are equal to Kc, products over reactants. Now this is where we use stoichiometry to help us out. So let me just change color and we'll tabulate then what we were given in red, and now let's go to work in what we can deduce. We know that reactants get used and products get made, and that they do so using their stoichiometric value. Let's let the value of hydrogen that's consumed represent letter x, our variable. And I'm also going to let that be representative of iodine. They have a 1-to-1 stoichiometric ratio. And in our ice chart, what we've now determined, at equilibrium, we have a value of 1 minus x for hydrogen, and at equilibrium, we would have a value of 2 minus x for iodine. Keep in mind the product got made, so it is going up in value, and it's going to happen at twice the rate. So 2x is going to be its molar concentration, 2 to 1-to-1 ratio. So at equilibrium, we have a value of 2x. So let's begin with a little bit of algebra, knowing what we are given and what we're trying to solve for. The product here, HI, will go on top and it will be squared, set over the concentrations of our reactants, all equal to the K value. If 50.5 is our given constant, it will be equal to the molar concentration at equilibrium of our product, 2x, squared due to the stoichiometry, set over the equilibrium concentration 1 minus x for hydrogen, set equal to the equilibrium concentration of iodine, 2 minus x. We need to solve for x. Go back and plug in and we'll have those concentrations. First thing that I'd like to do is to just simply FOIL, distribute through these parentheses. So 1 times 2 is 2. 1 minus x. And then inside we get minus 2x. And then x times x would be plus x squared. So to simplify, here's what we know. 2 minus 3x plus x squared is simplifying these two parentheses, isn't it? That's just that term you're probably very familiar with. We FOILed first, outer, inner, last, simplifying. So continuing through this 2 minus 3x plus x squared, I have to now distribute. So let me just kind of simplify what we have so far. This is going to be brought up. 2 minus 3x plus x squared is equal to, so I'm just bringing this to this side. Now we have 2x, both are being raised to the power of 2, so remember that's actually 4x squared. Alrighty. Let's distribute 50.5 through this parenthesis. So to your calculator, 50.5 times 2 equal 101. 50.5 times a negative 3 to hit that twice. And I found negative 151.5. And that still retains the x. Plus 50.5 times x squared is 50.5 x squared equals 4x squared. Now we're trying to bring the like terms and set equal to 0, so we have a quadratic equation. We can have a value of a and a value of b and a value of c to plug into our quadratic equation formula. So we have to bring the 4x squared to this side. So I'm going to subtract 50.5 minus 4, and we get 46.5. So let me rewrite 101 minus 151.5x plus 46.5 x squared equal 0. Now we have the following. We have an A, which is positive 46.5. It's not very neat. Let me try to make that better. 46.5. The value of B is negative 151.5, and the value of C is positive 101. Now let's hit down our quadratic formula. All right, so under my programs, I have a program called Quad, and what I literally do is type in the values for A. So for A, I'm going to type in 46.5, enter. My value of B, negative 151.5. And my value for C is positive 101, and I hit enter. And I get two different values for my x, and I'm going to write them both down and then talk you through our decision. One possible value that's given to me is 0.9349, so I'll say 0.935. And the other value given to me is 2.32. How do I determine which one of my two possible choices makes sense? And I want you to go back to the original grid, because always when we're solving a quadratic equation for an equilibrium constant, one of the answers makes no sense. In other words, perhaps it even comes out negative, and we all know there's no such thing as negative pressure or negative concentration, so always toss out the negative choice. But here my answers were both positive, 0.935, 2.32. Keep in mind, the 2.32 is too large for what we're solving for. I can't start with 1 mole of hydrogen and use 2.32 moles up and have a negative value here. Again, if I start with 2, I can't use up 2.32 and end with a negative value. That number is too large, and therefore we know we can eliminate it. X must be the one that makes sense of the two choices when comparing it back to the actual grid. Remember, this isn't what we were asked to solve for ultimately. What we were asked to solve for is the equilibrium concentrations. So we need to go back and fill out this row. 1 minus 0.935. 2 minus 0.935. And over here, the value of 2x would be 2 times 0.935. And let's hit that out. 1 minus 0.935 gives us an equilibrium concentration of hydrogen as 0.065 atmospheres. Or excuse me, these are molar concentrations, so moles. 2 minus 0.935 gave us a value of 1.065 mole units. And 2 times 0.935 gives us an equilibrium concentration for the HI as 1.87 molar units. So my three answers: the concentration of HI, 1.87. The concentration of iodine, 1.065 moles. And the value for the hydrogen, 0.065. We've done for the first time a quadratic equation. I know I'm going to need those if I'm given the known value for Kc and just two concentrations. I've given information up here in the ice, the initial row. So I have to use x's to determine how much of the product was made, how much of the reactant was consumed, and let those variables play a role in the equilibrium row. But these end up getting placed up into the expression, and using a little bit of algebra, we're able to solve for the equilibrium values. Let's try another. We have 200 atmospheres of nitrogen mixing with 100 atmospheres of hydrogen at 250 Celsius degree. Find Kp at the same temperature if the final pressure of the system is 239 atmospheres, and then we can find for Kc. Well, here's what we start with. We always get our recipe written. We have molecular nitrogen plus molecular hydrogen in dynamic equilibrium for the production of ammonia, the Haber process. If 200 atmospheres are mixed with so we have 200 atmospheres, 200 for nitrogen. We have 100 atmospheres for hydrogen, and of course there would be no product yet made. But a little different. We're not given Kp, we're not given Kc. What we're given here is the total pressure. This looks like a Dalton's law of partial pressure. If the sum of all of the partial pressures at the end is 239, here's what it's really saying. And I'm going to just kind of finish this grid. Here's what we know. Alrighty, so in blue, they just kind of tabulated what we know, and I'll go ahead and start using red. We know that reactants get used, products get made, and I better balance my equation before I go much further. A 1 to 3 to 2. Let's let the letter X represent the amount of nitrogen consumed. I like X because it has the coefficient of 1. So of course we're going to see the nitrogen partial pressure drop by a factor of X. So at equilibrium, we have a value of 200 minus X. Now see what will happen is hydrogen gets consumed at a rate of 3 times the value of nitrogen. So want over given, we're going to say this goes down by a value of 3x. So at equilibrium, we have 100 minus 3x, representing the partial pressure of hydrogen. Of course, products get made, so it will have a value, and it will have a value of 2x, twice the value what we had for nitrogen. And so at equilibrium, this has a value of 2x. Now, what's different in this problem compared to the last problem, we're given partial pressures and we're given the total. We're not given Kp or Kc. What we're given is the total pressure. So let me kind of clarify that, and I'll use green. At equilibrium, the pressure of the nitrogen, when added to the pressure of the hydrogen, when added to the pressure of the nitrogen, they combine to give me a total pressure of 239 atmospheres. That's what total pressure means, the sum of the individual partial pressure. We learned this in our gas laws as Dalton's law of partial pressure, that the total pressure, I'm going to just use PT, is equal to the sum of the partial pressure of nitrogen plus the partial pressure of hydrogen plus the partial pressure of ammonia. Dalton's law of partial pressures. We know the total pressure to be 239 atmospheres. We know the partial pressure of nitrogen to be 200 atmospheres minus X plus the partial pressure of hydrogen, which is 100 minus 3x, plus the partial pressure of ammonia, which we let represent 2x. Let's combine our like variables here. We have two numbers here. We have 200 plus 100, and over here we have 239. So let's just kind of go slow with algebra. 239 equal 200 plus 100 is 300. Minus x minus 3x is minus 4x plus a positive 2, so that brings us back to 2x. No, it doesn't. It brings us to minus 2x. Always nice to have an algebra buddy. Minus x minus 3x is negative 4 with a positive 2. We're left with a negative 2x. Let's bring this side over. So 239 minus 300. And there I found negative 61 equal x, equal negative 2x, that side over here. So negative 61 divided by negative 2 gives us x. And x came out to be a value of 30.5. So what does that mean? Up here, x was 30.5. So minus 30.5 gives us our equilibrium pressure of 200 minus 30.5, gave us 169.5. I'm going to jot that there. Those are atmospheres. 100 minus 3 times 30.5 hit that with me, 100 minus 3 times 30.5 leaves me with the value of 8.5. So the x here, I'm just putting in 30.5. 3 times 30.5 is, oops, I hit that wrong. 30.5 times 3, we find 91.5. 100 minus that answer is 8.5. So I checked that twice. And here we'll have 2 times the value of 30.5. And so 2 times 30.5, did you find with me? 61. Because now we have those equilibrium pressures that we can quickly calculate a Kp from. So Kp can be found by taking the partial pressures at equilibrium of ammonia, which was 61. It needs to be squared, set over partial pressure of nitrogen, which is 169.5 to the first power, and the partial pressure of hydrogen, which is 8.5 at equilibrium, cubed. Let's hit for Kp. 61 squared divided by 169.5 equals, divide again by 8.5 cubed, and my Kp I found 0.0357. So 0.036 would be fine as well. Kp. Were we asked to solve for Kc as well? So that goes back to one of those very first equations that we had to convert Kp from Kc, and it had to do with the delta N, products minus reactants. And so way back to the beginning of your first page of your notes, somewhere in there, you were told how to convert Kps and Kcs. I can't remember exactly where. I'm going to guess toward the bottom of your, oh, here it is. Perfect. Good work. Kp equal Kc, R times T. R is the gas constant, 8.31, raised to the delta N, where delta N is the change in number of moles of a gas, which is product minus reactants. So this is where we'll have our Kp value we just calculated. We're going to pull out Kc using R. You know what? R is in atmosphere, so it's 0.0821, and Kelvin temperature. So help remember that, Kc RT delta N. And go ahead and plug that in. You've got that ability here. Here's your Kp. R I want you to use is 0821. Kelvin temperature would be 250 plus 273. 250 plus 273. Alrighty, so R times T, and the delta N, remember what we would do is products minus reactants, so it would be 2 gaseous moles minus 4 gaseous moles, so you'd be raising it to the -2 power. Please figure that out for me. Using your algebra skills, we have a Kp equal Kc RT delta N, and I've given you the variables. Kp is 0.0357. We'd like to solve for Kc. We're going to match the gas constant to the atmosphere, so 0821. Kelvin temperature is 250 plus 273, so that's 523. All raised to the -2 power. What do you find? Hit for that. 0821 times 523 equal, raised to the -2 equal. So now I'll go 0.0357 divide by answer, and I found a Kc equal to 1.921 times 10 to the negative fifth. How about this one? Looking at the last one here, we're on page 9 still on our notes. How about this one? Sodium bicarbonate can be decomposed with heat to what three products? Well, sodium bicarbonate, NaHCO3, is sodium bicarbonate, and it decomposes to give three products. What will happen? You'll produce sodium oxide, Na2O, the metal oxide. You'll produce carbon dioxide, and you'll produce water. Now these are solids. Sodium bicarbonate's an ionic compound. Sodium oxide is an ionic compound. They're always solids at room temperature. But assuming that we're heating these to be, to force the decomposition, carbon dioxide and water both will come out as gases. We better do some balancing here. 2 NAs, 2 NAs, 2 H's, 2 H's, 2 C's, 2 C's, 6 oxygens, 1 plus 4 is 5, plus 1 more is 6. So it looks like a 2, 1, 2, 1, the way I have it written. Kp is given to us as 0.23. Find the total pressure of gas in this equilibrium. Well, we have some pure solids, don't we? And we know that they're going to fall out of our equation. So the expression for Kp simply looks like the partial pressure of carbon dioxide squared, due to its stoichiometry, times the partial pressure of water, which is water vapor here. It's gaseous water, so it's being included. If this were a little L, it would definitely drop out. But look at the temperature. The temperature that was provided to us was quite high in this. Let me get back to where it was quite high in our equation, and so therefore I knew based on its based on the temperature that it was going to be, in the gaseous form. So let's see if I can get where I want to be here. Great. Pulling this down, and now I've hidden it. Oh, Linda, there we go. There we got it. Thank you. Let's do the following. We have dropped out the solids, and we know the Kp. So Kp is equal to 0.23. Since these were indeed equilibrium, find the total gas pressures at equilibrium, let's let the value of the water be x. And the reason I'm picking water at equilibrium to be x, because it has a coefficient of 1, and then therefore I can let this value at equilibrium be a value of 2x. I have twice the number of gas particles of CO2 as I do water. So in the equation, the partial pressure of carbon dioxide we're letting represent 2x, and that needs to be squared still. It's still part of the formula, times the partial pressure of water at equilibrium, which we're letting to be x. 2 squared is 4. X squared is x, or x raised to the second power is x squared, times x. You get 4x cubed equal 0.23. Alrighty. 0.23 over 4 is x cubed. So raise that to the 1/3 power and you'll have the value of x. Let's do that math. 0.23 divided by 4 isolates the x cubed. So I raise that to a power of 1/3. That's taking a cube root, if you will. And x came out to be a value of 0.3859, let's say 0.386. And those are atmospheres. Alrighty. Remember the initial question wanted to know What's the total pressure? I need to add, don't I? We need to know the total pressure. So 2 times the value of x, 0.386. That represents the partial pressure of carbon dioxide plus the partial pressure of water, which was directly x, so 0.386. The sum of those individuals give me the total pressure. So 2 times 0.386 is 0.7719 plus the original x of 0.386. I'm finding the total pressure of our system equal to 1.157. I'll just do a little rounding. 1.16 atmospheres, the total pressure in our container at equilibrium. We've reviewed several different example problems, introducing the concept of an ice chart, introducing the concept of a reaction quotient, continuing our practice using a quadratic equation, and employing Dalton's law of partial pressure. I tried to work a wide variety of problems that you may encounter when solving equilibrium constant.